So in the today's class, we will discuss the collision theory of reaction kinetics. So how did collision theory try to explain, the occurrence of a chemical reaction, and why does a chemical reaction actually takes place with certain speed or certain rate. Okay, so it tries to give an expression for rate constant of the reaction, and comparing the rate constant predicted by the collision theory with the experimental rate constant would indicate us the correctness of this theory. So the early stage, in the early stage, the collision theory was developed in order to explain the effect of concentration on the rate of the reaction. If you have a reaction A plus B giving product, the rate equation can be written as rate is directly proportional to concentration to the power A and concentration to the power B. Greater the reactant concentration, faster is the reaction. So it was not a surprise to propose that the rate of the reaction should therefore be directly proportional to the number of collisions taking place between the reactant molecules. Greater the concentration of the reactant in a reaction vessel, greater will be the number of molecules per unit volume, and therefore greater should be the number of collision between the molecules taking place per unit time. So the collision frequency will be directly proportional to concentration. Greater the concentration, greater the collision frequency, and therefore greater should be the rate of the reaction. To give an example, here I have given two cases. In one case where the concentration of the reactant is less, we have considered two molecules of A and two molecules of B. So one molecule of A can collide with the two molecules of B. Similarly, the other molecule of A also has the opportunity to collide with the two molecules of B. So altogether you have four collisions taking place per unit time or per second. Okay, so here we have ignored the other types of collision. Even you have collisions of the type AA or BB, but they are ignored because they do not undergo any particular chemical reaction. So it is only the collision between A and B that may result in a fruitful chemical reaction. So when the concentration is less, that is when the number of molecules per unit volume is less, the collision frequencies will also be less, and so is the rate of the reaction. But when the concentration of the reactant is very high, so what you observe, see here is I have doubled the concentration of the reactant. So instead of two molecules each of A and B, we have four molecules each of A and B. And it is easy to understand that each molecule of A can collide with four molecules of B. So overall, you can expect 16 collisions to take place per second. Okay. So greater is the collision frequency when you have greater number of molecules or greater concentration of the reactant. So the collision theory that was developed in the earlier stage assumed that the rate of the reaction, or rather the rate constant of the reaction, should depend on the number of collisions taking place between the reactant molecules per second. Okay, so according to collision theory, the rate of the reaction, in fact the rate constant of the reaction, the rate constant of the reaction K depends on ZAB, that is the number of collisions between the molecules of A and B per unit volume and per unit time. So the collision theory assumed that for a reaction to take place, the collision between the reactant molecule is a must. It is the necessary criteria for a reaction to take place, and it is the only criteria for the reaction to takes place. So this is the earlier version of collision theory. That is why this theory is called collision theory. So according to this theory, therefore, for a reaction to takes place, the collision between A and B is a must. In the earlier version of the theory, it was believed, it was believed that the collision is the only factor that decides the rate of the reaction. So what does collision theory assume is, if there is a collision between A and B, then it should result in the formation of the product. So when molecules A and B collide, the first collision itself should result in the formation of the product. So rate constant K is equal to ZAB. So according to collision theory, the rate constant of the reaction is equal to the number of collision taking place between molecules A and B per unit time, that is per second, per unit volume. Each collision should result in the formation of product. It should undergo a chemical reaction. So how to calculate ZAB? So the number of collision between the molecules A and B is calculated. You can calculate ZAB, or you can predict its value. Predict is predicted by using kinetic theory of gases. You have studied this kinetic theory of gases in your undergraduate course. So by using the kinetic theory of gases, it is possible to predict or calculate the number of collision taking place between the molecules A and B per unit volume per unit second. So since we have used this kinetic theory of gases, it should be very clear that this collision theory is largely applicable for the gaseous reaction. It is somewhat approximately applicable for reactions in solution. It is largely applicable for gaseous reaction. Now the problem with this theory is, this theory is based on the fact that each and every collision between the molecules is a fruitful collision. What do you mean by fruitful collision? When the molecules A and B collide, they immediately undergo chemical reaction. So theoretically, the number of collision taking place between the molecules per unit time, per unit volume is very, very large. For example, if I mix a few millimoles of A and few millimoles of B, what do you mean by a millimole? It is 6.023 into 10 to the power 20 molecules of A and 6.023 into 10 to the power 20 molecules of B. So when you are mixing up such a large number of molecules, the collision frequency should be very, very high. And since the first collision between the molecule itself results in the formation of the product, therefore the rate of the reaction should be very, very, very high. Therefore all the reaction should take place with much greater speed. Because the first collision itself should result in the formation of product. For example, if there is 10 to the power 20 collisions taking place in unit second, and each of these collision results in the formation of the product, you may expect a chemical reaction to get completed in a few seconds. So the rate of the reaction, or the rate constant of the reaction, should be very, very high as predicted by collision theory. The second problem with this theory is, since the number of collision depends only on, since the rate of the reaction only depends on the number of collision, it may possible that all the reaction proceeds with almost same rate. Yakandre, irrespective of the nature of the reactant molecules, the number of collisions taking place between the molecules may be almost one and the same. So different reactions should proceed with almost the same rate. which is not possible. We know that most of the organic reactions are very slow and they are not fast as predicted by collision theory. The second observation that we have and experience we have is not all the reactions proceed with same rate, but according to collision theory, okay, almost all the reactions should proceed with nearly same rate, because the rate of the reaction depends only on the collision frequency, and the collision frequency will be almost same for most of the organic reaction. So both the facts are not true. Not all the reactions are very fast and not all the reactions have same rate. So it is very clear that the rate of the reaction is not decided by the only one factor, that is collision frequency. So this is the important failure of collision theory. So this is an earlier version where it was believed that rate only depends on collision frequency and each collision is a successful one. So the theory, after experiencing failure, okay, it was modified and a modified version of this theory was proposed. This postulate, okay, largely concentrates on the effect of concentration of the reactant. So according to collision theory, only the concentration of the reactant is the deciding factor, okay, which is actually not true, because there are other factors that affect the rate of the reaction, such as temperature. So the collision theory borrowed the idea of Arrhenius. Okay, what is the idea of Arrhenius? It is the concept of activation. So a modification was made to the collision theory. So they postulated that not all the collision taking place between the molecules are a successful collision. Only a few collision out of large number of collision may result in the formation of product. So how to consider or define a successful collision? They defined a successful collision as the one in which the molecules acquire that minimum extra energy called as activation energy. So only those collisions in which the molecules get activated by acquiring that minimum excess energy called activation energy, only those collision may result in the formation of product. So they borrowed the idea of Arrhenius, that is the concept of activation energy. Only those reactions or only those collisions result in the formation of the product in which the molecules are capable of crossing the energy barrier. So they modified this equation, okay, by introducing this Arrhenius pre-exponential factor e to the power minus Ea by RT into equation 1. So what is equation 1 stating? Okay, you can state this equation 1 as, therefore the rate of the reaction should be equal to number of collisions per unit second per unit volume. Okay, this is the statement of equation 1. Now what modification they made to this theory or model is, they assumed that, okay, not all collisions are successful ones. Okay, out of ZAB number of collisions, only few can be considered as successful collision. Okay, so how to consider which are successful ones? Only those collisions in which the molecules acquire a minimum excess energy called activation energy, EA. Only those collisions in which the molecules acquire a minimum excess energy called activation energy are effective in bringing about the chemical reaction. Therefore, equation 1 is now modified and written as K is equal to ZAB, that is the collision frequency. It is now multiplied by a exponential factor, and this exponential factor is borrowed from Arrhenius equation, that is e to the power minus Ea by RT. So this value is very high. Okay, as I already told you, ZAB is very high, and since ZAB is very high, in equation 1 K's rate constant is also very high, abnormally high than the experimental value. But multiplication of this ZAB by this number, okay, and this number is very small because you have exponential to the power minus term, so this number is very small. So when you are multiplying this large number by a very small number, so what happens, overall this number becomes less compared to this is now very less. So what they have done is they have reduced the theoretical value of K. Okay, so they wanted to reduce the abnormal value of K, and now they are successful in reducing the value of K by multiplying this by exponential factor, which is nothing but the Arrhenius term. So this ZAB, that is the collision frequency, is similar to the Arrhenius factor A that we have in the Arrhenius equation. So equation 2 is now stated as, therefore according to collision theory, the rate of the reaction is equal to the number of effective collisions or active collisions taking place per second per unit volume. So you can see or note the difference between these two sentences. Earlier it was proposed that the rate of the reaction should be equal to the number of collisions per second per volume. It means each collision results in the formation of the product, undergoes chemical reaction. Now you can see the modification made here. The rate of the reaction is equal to the number of activated collisions, okay, activated collisions taking place per second per unit volume. So not all the collisions result in the formation of the product, only those collisions called as activated collisions in which the molecules acquire the minimum excess energy called activation energy can undergo chemical reaction. So this total activated collision taking place per unit second per unit volume is very less than the number of collisions. So there is a significant decrease in the value of rate constant now predicted by collision theory. But what it was observed that still yet after making modification, okay, the theoretically predicted value of rate constant is much higher than the experimental value. So they concluded that these two factors are not the only factors that affect the rate of the reaction. So earlier it was proposed that rate is directly proportional to collision, then it was modified and postulated that rate is directly proportional to the number of activated collisions. So these two factors, that is concentration of the reactant and concentration as well as temperature, okay, here both the factors are included. So these two are not the factors, the only factors that control the rate of the reaction. There is some other factor, okay, that has a control over the rate of the reaction. So they made further modification into equation 2 and they introduced a term or a factor called as probability factor or steric factor. So what is this probability factor or steric factor? So the purpose of introducing this probability factor or steric factor is to reduce the theoretically predicted value of rate constant K. So what is this probability factor? Let us understand. According to the second equation, equation 2, what is the rate predicted by collision theory? It is equal to the number of activated collisions per second per unit volume. So the only criteria for a reaction to take place according to equation 2 is the molecules should get activated during collision, and if the molecules get activated during collision, each such activated collision should result in the formation of product. But really, do activated collisions result in the formation of product? Whether all the activated collisions are successful collisions or not, The answer is no. Not all the activated collisions are successful collisions. We cannot consider all the activated collisions as a successful collision resulting in the formation of the product. Why? Because along with this activation, there is one more criteria the collision should satisfy, and that criteria is when the two molecules collide, they should collide with proper orientation. Okay, if the molecules do not collide with proper orientation, and even though they are activated, if they do not collide with proper activation, they may not result in the formation of the product. They in fact will not result in the formation of the product. I'll give an example. For example, if you are considering a nucleophilic substitution reaction, okay, so you have, okay, a leaving group, okay, which is a nucleophile, and you have an attacking group Y minus. Okay, so let us assume that these two are rigid spheres, okay, sphere like structure. Now this nucleophile, the attacking nucleophile, may attack this substrate from any direction. Okay, Y minus can attack from this direction, Y minus may attack from this direction, or it may attack from this direction, or it may attack from this direction, or it may attack from this direction. And the collision between the substrate and the nucleophile in any direction may be an activated collision. For example, this collision may result in an activated collision, or this collision may also result in an activated collision. But in spite of this happening to be an activated collision, the reaction will not take place. So though the molecules are activated on collision, the reaction will not take place because the molecules has to collide with the proper orientation. And what is the rule of such a nucleophilic substitution reaction? That the incoming nucleophile or the attacking nucleophile should attack the substrate from a direction which is exactly opposite to the leaving group. Okay, so the for a reaction to take place, nucleophilic substitution reaction takes place, the attack of the nucleophile should be only from one direction. That direction is exactly opposite to the direction in which the leaving group leaves the substrate. Any other direction will not result in the formation of chemical reaction, though the molecule is getting activated. So you have large number of collision in all directions. Say for example, there are 1000 collisions, okay, that is taking place between substrate and the nucleophile, and out of 1000, say for example, in 50 cases the molecules are getting activated. So out of 1000, only in 50 cases the molecule is getting activated, so the remaining 950 are ineffective collisions. And even in this 50 activated collision, there are only few collisions taking place in the proper direction. Say for example, there is in this case only one collision taking place in the proper orientation. So even though there are 1000 collisions taking place per unit second, out of 1000 there are only 50 activated collisions, and out of the 50 activated collisions there is only one activated collision taking place with proper direction. So you can see that out of 1000 only there is one effective collision that results in the formation of product. So this is equal to ZAB, that is collision frequency. This is equal to ZAB into e to the power minus EA by RT. So it is the number of activated collision. Now here we have multiplied this activated collision by a factor represented by P, which is called a steric factor or probability factor, which has reduced this activated collision into only one effective collision. So generally this probability factor or the steric factor is very less. Why it is less, you can understand, because even though there are 50 activated collision, there is only 1 out of 50 which is effective collision. So thereby the rate of the reaction should be much less than that predicted by equation 2. Equation 2 in all the activated collision should result in the formation of the chemical reaction. So now we have to modify this equation, and postulate that only those activated collisions in which the molecules collide with the proper orientation, only such collisions should result in the formation of the product. So collision theory was again modified, okay, because this equation 2 does not give a justifiable answer. We are modifying this equation 2, and a modified collision theory states that only those activated collisions taking place per second per unit volume in which the molecules are colliding with proper orientation, that is in proper direction. Okay, so only those collisions in which the molecules are colliding with proper orientation results in the formation of product. So only such collision undergo chemical reaction and result in the formation of product. So the rate of the reaction is, okay, this is the activated collision. It is now multiplied by a factor P called as Steric factor or probability factor. So what does equation 3 tells? Equation 3 tells therefore the rate of the reaction is equal to the number of activated collisions per unit second per unit volume taking place with proper orientation. So this is the final version of the collision theory. K is equal to P into ZAB into e to the power minus EA by RT. This is the effect of concentration, that is collision frequency. This is the effect of temperature. So altogether this represents the activated collision. P represents the collision, the probability factor. So if I multiply this probability factor to this activated collision, it represents the effective collision. So the value of P generally varies from 1 to as low as 10 to the power minus 8. According to collision theory, the value of this probability factor varies anywhere between 1 to 10 to the power minus 8 depending on the chemical reaction. So for some chemical reaction, probability factor may be as high as 1. What do you mean by probability factor is equal to 1? It means that each collision takes place with in proper orientation. So the molecular structure is very simple, that if the molecules are colliding in any direction, that is a correct direction or correct orientation. So all such collisions are effective collisions. So in such case probability factor is very high, almost equal to 1. What do you mean by 10 to the power minus 8 probability factor? It means out of 10 to the power 8 active collision, only one collision takes place with proper orientation. So out of 10 to the power 8, just one collision results in proper orientation. So the value of probability factor depends on the structure of the reactant molecule. If the structure of the molecule is much complicated, the probability factor is very less. So and if the probability factor is very less, the rate of the reaction will also be very less. Okay, so this is the final version of the collision theory. The advantage of collision theory is it gives a very simple picture of how the reaction takes place and what are the different factors that affect the rate of the reaction. Though this is a very simple version or a simple theory, it has several limitations. Okay, so what are the limitations of collision theory? Let us understand. And we have more limitations than advantage. The first limitation of this theory is it is only applicable for gaseous reactions. Okay, the value of ZAB, that is collision frequency, was estimated by using kinetic theory of gases. So what does it mean? It means that this theory is useful in predicting the rate constant of reactions taking place in gas phase. It is less applicable for reactions taking place in solution. The second limitation of this theory is, despite of several attempts to reduce the theoretical value of rate constant, it is observed that still the rate constant predicted by collision theory theoretically is much greater than the experimental rate constant. So theoretical value of K predicted by this theory is much greater than experimental value. Okay, so we a lot of efforts were put to reduce the value of K. Okay, earlier equation 1, it was assumed that K is equal to ZAB and a very high value of K was obtained. So attempts were made to reduce the value of K by multiplying it by this Arrhenius factor, but still it yielded a much higher value of K. Further attempts were made to reduce the value of K further by multiplying this activation collision by probability factor. So in spite of all these attempts, still the value of K predicted by this theory is much larger or greater than the experimental value. And the difficulty of this theory is, it does not exactly tell us, okay, the procedure for calculating this probability factor P. If I am given a particular reaction involving particular reactant molecule, okay, by looking at that reactant molecule, we do not know a experimental method or a theoretical method to calculate the value of P. So without knowing the value of P, it would be rather difficult to get a theoretical value of K. So this is another important limitation. This theory does not mention the method for predicting the value of probability factor P. Okay, it is not possible for this theory to give an explanation or a method using which one can estimate the value of the probability factor for a particular reaction. It just says that the probability factor should vary somewhere between 1 to 10 to the power minus 8, but exactly what should be the value of P for a particular reaction, there is no method for estimating. Okay, the fourth limitation of this theory is, here EA represents the activation energy. Okay, so what does it say is, when the molecule get activated, okay, it means the molecule is having now excess energy, okay, than the normal molecule. So when the molecule is having excess energy, that energy is manifested in which degree of freedom. Okay, a molecule's energy may be invested in its different degree of freedom. What do you mean by degree of freedom? It is the different modes of motion. Okay, for example, a molecule may be undergoing a translational motion. It means it has translational or kinetic energy. A molecule may be rotating. It may have rotational energy. The bonds present in the molecules may be vibrating. It means the molecules has vibrational energy. Similarly, the electrons are revolving around the nucleus of the atoms inside the molecule. It has electronic energy. So there are different degrees of freedom. There are different modes of energy a molecule can have. So when the molecule gets activated, okay, in which energy mode it is actually getting activated, whether there is an increase in rotational energy, or whether there is an increase in vibrational energy, or whether there is an increase in electronic or translational energy. Okay, that is the question. According to collision theory, okay, it predicts that when a molecule is getting activated, it is actually the translational energy or the kinetic energy of the molecule that is getting activated. But since the molecule is having other internal energies such as rotational energy and vibrational energy, the very reason, okay, to consider only translational energy is not explained. So even though the molecule is having other internal energy, they are totally ignored. Okay, that is the fourth disadvantage or limitation of this theory. The activation energy is associated purely with respect to the translational energy, that is kinetic energy of the molecule. Okay, the activation energy is associated purely with respect to the translational energy or kinetic energy of the molecule. Other forms of energies such as rotational and vibrational energies are totally ignored. Okay. One more important limitation of collision theory is it cannot explain the kinetics of unimolecular reactions. So reactions involving single molecule or one type of reactant molecule such as isomerization reaction or decomposition reaction. Okay, so the kinetics of such unimolecular reactions cannot be explained by collision theory. So we require an entirely a separate theory for explaining the kinetics of unimolecular reactions. So because of these limitations of collision theory, though this is a very simple theory, but because of so many limitations, we have to discard this theory, and a new theory, okay, is proposed, which is called as activated complex theory or transition state theory. And this theory is the most successful theories of chemical kinetics, and currently we still use this transition state theory, activated complex theory, in almost the same form which was proposed much years back. Okay, of course several modifications are made to this theory, but the original idea of theory is almost the same. So the transition state theory or activated complex theory successfully explains the kinetics of a chemical reaction. So what is this transition state theory or activated complex theory is very now important. So we will learn about this theory called as activated complex theory or transition state theory later, but in the next class, first we will concentrate on this kinetics of unimolecular reaction. So why collision theory fails to explain the kinetics of unimolecular reaction. Then we will discuss two mechanisms or two theories that were proposed to explain the kinetics of unimolecular reaction. The two theories are namely Lindemann's theory and Hinshelwood's theory of unimolecular reactions. Okay, after studying the unimolecular reactions, let us again come back to the transition state theory or activated complex theory.